So, so today I prepare a talk about agent-based modeling. So I will present how we can use this agent-based model to study opinion dynamics or norm formation. And if you have any questions, you may ask them, interrupt me and ask them if something that is not clear, or you may wait to the end of the presentation. Okay, so the plan of today's talk is as follows. So first of all, I would like to present some basic concepts behind agent-based modeling. So I will present components of an agent-based model. And one component of such a model is a network in which our agents are placed and in which they interact. So I will define different networks that we can use in this purpose. And later on, I will talk about different models of opinion dynamics. I will focus mostly on nonlinear Both-or model. Why? Because first of all, this model is widely used in modeling opinion dynamics. Also, this is quite simple model, so we can follow how it behaves and also analyze it analytically. And also, this is the model I work with. So I will present the definition and also different modifications that originates from this model. And the main idea behind this talk is to show you how we can analyze such artificial social systems, how we can study opinion dynamics. So I will tell you what questions we ask when we analyze such models, what tools do we use, and I will show you also different approaches to model agents' behavior. So yes, so let's start with this general idea of agent-based models. So the idea is that we have a system of many interacting parts, and these parts are called agents. And of course, depending on the phenomenon we want to simulate, we want to study, these agents may be represented by individuals, so people, voters, or customers. But also agents may be whole groups of people, of individuals like households, different institutions like banks, different firms, and so on. Since we analyze opinion dynamics, as our agents, we will have voters or people with some opinions. Next, we have to set our agents in some environment. And of course, here we can use some physical space with a notion of dimensions. Like, for example, if we would like to model some flock dynamics, we most likely will place our agents in two-dimensional or three-dimensional space. But what we most commonly do in the field of opinion dynamics, instead of using this physical space, we use some conceptual network. And this network represents some kind of possible interactions that may occur between agents in our system. So we used here social networks, some networks that represent friendships. And the last part that we have to define are the interactions. So here we can do this by introducing different functions. And how it is done is that agents try to maximize or minimize these functions by their choices, by their behaviors. So in economics, we use cost or utility functions. Cost functions are minimized, whereas utility functions are maximized. When we talk about physical systems, when we can introduce some kind of energy of the system or Hamiltonian, then the components of the system behave in such ways in order to minimize the energy, for example. Another thing, another way of doing that, we can just, instead of defining these functions, we can just say directly what are the rules that agents has to follow. So dynamical rules, and such as systems which are defined in such a way are called dynamical models. And we will focus on dynamical models. I will show you later on what are these rules in the case of voter model. So how we create simple models? So first of all, we have to choose a network topology in which we will place our agents. And we do it in such a way that with each node of that network, we associate one voter or one agent, and we let our agents interact through links in that network. So here we have a very simple example of a network in which all the nodes are connected with each other. Yes, and what we are trying to do is to find out what is the system behavior. So one question we would like to answer is how the results of our simulations, of our model, depend on the network topology. More general, what these results depend, how these results depend on different features of network or different characteristics. And to do that, we can simulate our model on different networks. So traditionally, models from statistical physics were analyzed on regular lattices. These lattices are characterized by high degree of periodicity or homogeneity. For example, here we have square lattice, or we clearly see the spatial pattern. All nodes have the same number of connections for neighbors. So this is highly periodic and homogeneous structure. Another thing we can do, we can just use some random networks. For example, we start with nodes that are disconnected, and with some probability we connect them. And then we, in such a way, we create a purely random network. But the problem with regular and random networks is that they do not have features that we can find in real networks, real social networks. So, and since we want to analyze opinion dynamics, something which happens on social structures, we would like our networks to resemble these characteristics. So in order to do that, we use complex networks. And the strict definition, there is no strict definition of complex networks. But what we can say about them is that they have some degree of regularity, but also randomness. And thanks to that, they are not fully periodic, but we can see some structure in these networks. And they are also not heterogeneous. For example, here we see an example of a network that represents protein-protein interactions. And we see that nodes have different number of neighbors. We see some structure. So what kind of networks we can use to model our social interactions? So here are the examples. So first of all, we can use what we call small world networks. And these are the networks that are characterized by high clustering coefficient. And that means that in this network, our friends are very likely to be connected. So we have many triangles in that network. And another characteristic of these networks is that they have short average path length. That means that it's quite easy to move from one node to any other node in the network. So this average path we have to cross is small. And by path, we mean how many links we have to cross by going from one node to another. So here we can say that many social networks resembles these characteristics. Another type are social scale-free networks, and these are the networks that have power law degree distributions. Degree of a given node is just a number of neighbors. This node have number of links. So if we have scale-free networks, that means that in these networks we can find nodes with many connections that have many neighbors, and these are the nodes. These nodes are called hubs. So, for example, here we see nodes with many connections. This is the hub, and these examples of such networks are the internet or the WWW, so the World Wide Web. The last example of complex networks are multiplexes, so-called multiplexes. So these are basically networks of networks. So we have different layers of networks, and each layer of that network may represent different types of connections. One layer may be responsible for our connections in one online portal, another on the connection in other portal or in real life, and so on. So we have many layers. Each layer is responsible for other ways of contact. And of course, the question that arises here is how the results of our simulation depend on different topologies, different network, and different features. So these are the networks. But now the question is how we model opinions. So each agent in our network has an opinion on a specific subject, and opinions are represented by variables. And of course, these variables may be continuous or discrete. If we have discrete variables, we further on can distinguish between models with multiple state variables. Like, for example, we may have, as here we see, 7-point scale, which is commonly used in different surveys or polls. This is called Likert scale. Or even we can have binary type of opinion. So our variable can be only in 2 states. And many problems can be modeled in this binary scheme of opinion. Like, for example, voting, diffusion of innovations, or some competition in the market when we have 2 leading companies, for example. So these are the possibilities. And now let's focus on nonlinear voter model. So this is the model we are going to analyze. And this model represents how opinion information spreads in the society under the influence of conformity. So conformity is a social interaction. Later on, we will define how this interaction exactly works. And in this model, our agents have these binary opinions. So each agent can be in 2 states. Let's say I have opinion that is in 2 states, 1 or -1, and you may say that these states are positive, negative, yes, no, and so on. So in our network, we have n agents, and we let them interact through links in that network. So let's now take a look at the dynamics and these dynamical rules, how this model works. So this is part of a network we are going to analyze. This is only a small part of our network that consists of n voters and agents. And first step of the dynamics that is later on repeated is that we choose randomly 1 agent in this network. So let's say we've chosen this node. And now we look at the nearest neighborhood. Neighborhood in that network is defined by the network topology. So this specific voter has only 4 neighbors. And now we randomly choose only Q neighbors from this group. Q is the parameter of this model. In this example, Q is equal to 2. So among 4 neighbors, we choose only 2 of them. And this group of Q neighbors form a group of influence that try to exert some social pressure on our firstly chosen voter. So we can have different scenarios right now. First one is presented here. So the group of influence is unanimous and has different opinion to ours. And this unanimity in this model is necessary to exert this social pressure. And this is also some observation from empirical studies that people tend to conform more to the groups that are unanimous. So this is reflected in this model in this way. So if the group of influence is unanimous in opinion, then we change our opinion to the state of the group. So here we flip to stick to the group of influence. Another possibility is that the group is unanimous, but has the same opinion as we have. Then then nothing happens. The conformity, we may say that conformity occurs, but since we have the same opinion, nothing changes in the system. And the third scenario is that the group of influence is in disagreement. And this model is defined in such a way that in this case, we can anyway change our opinion to the opposite, but with some probability epsilon. So epsilon is another probability, another parameter of the model that may resemble some kind of noise in the system. So this was one formulation of the model based on these dynamical rules. But of course, we can also define this model mathematically, writing down the formula for the flipping probability. And flipping probability is the probability that a given voter changes its opinion to the opposite, given that we know the fraction of disagreeing neighbors with him. So this is this formula. The first term, this formula corresponds to this conformity. And then the second one is this probability that we flip under the condition that our group of influence is in disagreement. And this is how we can mathematically construct define the model. Later on, many modifications of that model showed up, in which this epsilon was set to 0, and also other types of social interactions were introduced, because here we have only conformity. Why? So to explain why, let's think what is the final state of this dynamics. So what will happen if we repeat this procedure, this algorithm many times? So in a finite system, we will reach a final state in which all the agents are in the same state. So since we have 2 possibilities of opinion, all the voters will end up or down. And these are called absorbing states, because when we reach these states, nothing changes in the system anymore, because we don't have any disagreeing neighbors. Yes, so the probability of our flip is equal to 0. And in such a system, we can measure what we call exit time, so the time to reach consensus, or exit probability. So this is probability that our system will end up with all voters in the up state. But thinking from the social point of view, the state of consensus, maybe it's not so realistic. So what we can do in this model to also obtain some states in which we don't have this consensus or full agreement is to introduce different kinds of interactions, social interactions. So in this model, we have only conformity, and conformity tends to order the system, increases agreement between our agents. But we can also introduce interactions that decreases agreement in the system. These are, for example, non-conforming interactions. And social psychologists distinguish between two types of non-conformity, that is, dependence and anticonformity. And now the idea is that if we will have two these types of interactions, conforming and non-conforming one, the competition between them will lead to some phase transitions, which we are going to study. So how to introduce these types of non-conformity? So one way is to use such a parameterization in which epsilon is equal to 0, to just simplify the model, not to have too many parameters, and introduce another parameter which tells us what is the level of non-conformity. So now our agents will act in a way that with some probability p will act as a non-conformist, and with some complementary probabilities as conformists. And one question we want to answer is that whether we will obtain some macroscopic differences between different types of non-conformity that are introduced into our system. So in fact, we can construct two different models, with one model with dependence and one model with conformity. So how it works? So the part with conformity works exactly the same as in the case of nonlinear Volter model, but what changes is this part of non-conformity. So with probability p, our selected agent will act independently from his neighborhood, and he may change his opinion to the opposite randomly with probability half. In the model with anticonformity, with the same probability, we act as anticonformists. And the way to do that is that if we have an influence group with unanimous opinion, we try to distinguish ourselves among this group, and we choose the opinion opposite to the group. And still in the case when the group is in disagreement, nothing changes in the system. So we have two models. In these two models, we have two parameters. One is the influence group size, and the second one is level of nonconformity. So what we are going to study in such a system, we are going to study how what we call order parameter. And in social systems, this order parameter is most commonly chosen as public opinion. Public opinion is just the average over all opinions of our agents. But very often we also rescale this public opinion to concentration of agents with positive opinion, because this concentration also tells us what is the probability that we will find an agent with a positive opinion. So it's easier to use this concentration with in calculations and also with analysis of the model. So what we want to study is how our system changes with time, how this concentration of positive agents change in time, what are the stationary states, so what are the final state of our system, how network structure or the dynamics, how these rules impact this behavior in our concentration. And finally, we want to study phase transitions. And phase transitions in this case, are defined based as true. Yeah. You have all people. In this model, S can be opinions of voters can be plus or minus 1. Yes. So if all of them are down, that means 0. Yes. Yes. Yeah. Sure. But yes, exactly. Yes, public opinion is from -1 to 1, and concentration is from 0 to 1. Yes, now it makes sense. Okay, so now we want to study phase transitions. So what are the phases in such a model? So phases are defined based on the value of order parameter. So we distinguish between two phases: ordered and disordered one. So disordered phase is when this order parameter is equal to 0. That means that we have equal number of voters in each opinion, with each opinion. So the system is disordered, both opinions are equally likely. Order phase is when this order parameter is different than 0. That means that one opinion dominates over the other. So that means that we have majority of voters in one state. And what we would like to do, and what we can have right now, is we can have two types of phase transition between these two phases. These are one type of them are discontinuous phase transition, and in discontinuous phase transition, the situation looks like this: that when we change some controlled parameter of the model, like in our case, this level of nonconformity in the system, we can observe some sudden change in the system. It's a sudden change in the system. Whereas when we expect continuous phase transition, the order parameter changes smoothly with this control parameter when we change it. So this is quite important to know in what system we can expect these sudden changes, and what system we can obtain this continuous phase transition, what properties of our system lead to this discontinuous sudden changes. And to find out this, of course, we can always simulate our models, but also it's nice to conduct analytical calculation, because then we can fully grasp the behavior of our model. So first approach in such modeling is to place our system on a complete graph, on the graph where all nodes are connected. And then we can use simple new field theory to obtain strict solutions. And this structure is not completely unrealistic, because it may model some small groups, small societies in which all people know each other. If we want to calculate something on complex networks, then we have use more sophisticated approximations, and very often we are not able to arrive at strict solutions. So then we may simulate our model, and we will focus on a simple example of complete graph. So how to give you just a basic idea how we analyze such a system. Everything is boiled down to writing down the rate equation. This is the differential equation that gives us the time evolution of our system. In this case, this concentration of positive voters. And to solve this equation, we have to find out transition probabilities. These transition probabilities tells us what is the probability that our concentration changes in such elementary by such an elementary value, and this value corresponds to one flip of one volter in the system. Now, depending on the network we use, on the dynamics, the difficulty is in writing down these probabilities. So the first approach is to write down mean field transition probabilities. And the mean field approach, in the mean field approximation, we assume that there are no fluctuations in the system and voters' opinion are independent. And thanks to that, we can easily write down these probabilities. So to follow this simple example, we can write down, assuming this independence of opinion and neglecting all the fluctuations, these transition probabilities can be write down directly looking at the algorithm of our opinion change, the system. So for example, in order to our concentration increase by 1, first we have to choose randomly agent that is down. This happens with probability 1 minus C. And then there are 2 mechanisms in which we can flip our system to be positive. So first one corresponds to conformity. Then we have to create an influence group that is composed of Q neighbors that are in state up. So that happens with probability C to the power Q. And then we can also flip under independence, and this happens with probability P times 1/2. So this is the way we can construct these formulas. And thanks to solving this equations, we can obtain some mathematical solution for the trajectories and for the stationary state. So here I present the time evolution of our system. These are typical time evolutions that we can see in our models. So first of all, I would like to draw your attention is that for small systems, this is one trajectory for a small system in which we have 200 voters. So we see that for a small system, we have big fluctuations that occur in the stationary states. But when we increase the number of agents for more and more, for larger and larger systems, these fluctuations diminish. And here we have much larger system for the same other parameters. And we see that for larger systems, the fluctuations in the trajectories are almost invisible. And also we see that that simulations, which are here depicted by dots, agree quite well with analytical solutions. So these are continuous lines. What more, we can see that here we see how system evolves starting from different initial conditions, from different fraction of adopted agents. And we see that eventually we can end up in different final states. These are called stationary states. And these stationary states, we see that depends on this fraction of this control parameter, which in our case is level of nonconformity. So what we would like to do is to plot how these stationary states depend on value of P. And these are the phase diagrams. And these phase diagrams we can also calculate exactly by setting our differential equations to 0, because this means that nothing changes in our system. So we see that this is the stationary state, nothing changes. What we can see more on these diagrams are dashed and continuous lines. So this correspond to stable and unstable states. Stable states are states in which, when we introduce some kind of disturbance, we will not fall out of these states. We will stay in this state. Whereas in the case of unstable states, so here we will just jump to other stable states. So now, since we know how more or less read these diagrams, we can present them for our two models. So the first is model with independence. And we see that in the model with independence, we have this possibility of discontinuous phase transitions. And whether we will get this discontinuous phase transition depends on the number of agents that try to exert this social pressure. So if this number of agents is greater than 5, then we can obtain discontinuous phase transition in such systems. Whereas we see that in the case of model with anticonformity, discontinuous phase transitions are not possible. So what we can learn from this model is that we see that one factor that promotes discontinuous phase transition, the sudden changes in the opinion, is independence. And another factor that promotes this discontinuous phase transition is the group size. So larger influence group size may lead to this discontinuity in the microscopic scale. Okay, so now, since we know how this model behaves and what are the results, let's take a closer look how the decision making occur in this model. So in our model, each voter can act as a nonconformist or a conformist with some probabilities. So in each time step, we may imagine that we flip a coin. On one side of this coin, there's nonconformity, on the other is conformity, and each time we flip this coin. And such a behavior that can change in time, such a variable that can change in time, in physics is called annealed randomness. And this annealed randomness corresponds to what we call the agent-based modeling situation approach to modeling agents' behavior, because we may look at it as that the varying conditions under which we take our decision impact our whether we are conformists or nonconformists. But another approach is to say that that our agents has some kind of personality. So in this case, at the beginning of our simulation, we can divide our agents into two groups. One group is composed of nonconformists, and all the other agents are conformists. So once again, we flip coin, but now we do it only at the beginning of simulations, and we assign agents to different groups. And this kind of randomness that is frozen in time is called ranged randomness, and this corresponds to this person approach in modeling opinion dynamics. And what is interesting, we can ask question whether these two types of approaches will lead to the same final behavior. And this answer to this question is not so obvious, because first of all, we use exactly the same distribution, the normal distribution in two cases. We also have, thanks to that, on average, the same number of nonconformist behaviors in both the systems. Yes, but the difference is only that in one system, this is frozen in time, this behavior. So what are the results? Okay, so how we can calculate, how we can find out the time evolution of our system is very similar as in the previous case, but in this case, we have two groups, so we assume that both of these groups um, have their own rate equations. We divide, in fact, our global concentration into a weighted average of concentration among positive agents in our two groups, conformists and non-conformists, and we construct rate equations for both the groups. And the idea behind how we construct these equations is exactly the same. So what are the results in the model with independence? We see that when we change this situation approach to person approach, where this behavior, where our agents have personality, then we see that, that this person approach eliminates all the discontinuous phase transitions and also shifts our diagram into higher values of independence. So we see that this effect is quite strong in this case. And this is what we call rounding effect. So that means that this continuous phase transition become continuous phase transition under the quenched disorder or quenched randomness. What happens in model with anticonformity? It's quite surprising because in this case, there is no distinction between these two types of randomness, and both lead to exactly the same result. Moreover, the phase diagrams for the case when we have this person approach are qualitatively the same as in the case of model with independence, but the diagrams are only rescaled. So what we see here is that this situation approach is another ingredient that can promote this continuous phase transition in our social systems. And right now we are working on a more general situation in which, instead of having this simple Bernoulli distribution, we can imagine that we have some arbitrary distribution of this level of nonconformity. So each agent has his own level of nonconformity, and we ask exactly the same question, whether we will have different solution in the person and situation approach. So this is one direction of my current studies. And another one is connected with interaction types. So at the end, I would like to say a bit about types of interactions. So we already know, I've already talked about interaction between agents, social influence, that we have different social influences, but I haven't talked a lot about interactions with the environment. So to model interactions with environment, there are some models that also include interactions with environment, but very often these interactions are modeled in the form of external field, very often fixed in time, whereas we know that in reality, change of some kind of norm, belief, or opinion may be related to some economical or behavioral cost that is very often changes in time, and also may depend on the number of adopters of a given norm. So in reality, we have such a feedback loop between social and physical world, whereas in modeling opinion dynamics, we don't see such a connection. So what we try to do is to go beyond these fixed parametric constraints and introduce to our models also some additional cost function that depends on the number of adopters. And one interesting point to study here is to look at the function that give a positive feedback when the number of adopters is low, and negative feedback when the number of when we have many adopters in our system, because then once again we can expect that competition between this negative feedback and positive feedback from social influence will result in phase transitions that we are going to study. So this is what I'm currently doing. So to conclude the talk, we already know that agent-based models are used to analyze many systems. And what we try to do by agent-based modeling is to set the connection between microscopic rules and macroscopic behavior of our model. We know that there are two types of phase transition, discontinuous and continuous one. And what we try to do is to find out what properties of our system leads to this discontinuous phase transition, because these discontinuous phase transitions are related to sudden changes in our system. And we already have some indications when we can expect these discontinuous phase transitions. So, for example, we know that independence may cause this discontinuity, larger influence group size. I haven't talked about that, but we also know that more layers in the multiplexes also promote these behaviors, situational approach. And right now we are dealing with different cost functions, and we also try to find out what are the features of that cost functions that will lead to discontinuous phase transitions. So thank you for your attention. If you have any questions, you're welcome.